Fisher is one of those scientists who makes everyone else look bad. Not only was he one of the greatest evolutionary biologists of his day, he was a phenomenal statistician, geneticist, and eugenicist to boot, transforming the fields of biostatistics and population genetics in the post-Darwin era. Born in East Finchley, London, Fisher was the youngest of 5 doting siblings, who, despite the hardship of extremely poor eyesight, thrived in school from an early age. His vision was so bad that he was forced to learn mathematics without the aid of paper or pen. Though this disability would later become an asset, he learned instead to visualize problems in geometrical terms, often to the wonder of teachers and classmates. At 19, he won a scholarship to Cambridge, where his interest in evolution led to the study of Mendelian genetics. It was at this time that he began to recognize the value of statistics in biological events, a concept that would drive his extraordinary career. It was only by luck, however, that he was able to immediately continue working. Graduating in 1912, in anticipation of World War I, Fisher tried repeatedly to join the army, only to be rejected repeatedly due to his vision. As a result, he spent the next few years working as a statistician for the City of London and later at the Rothamsted Experimental Station. The highlights of his career are too numerous to name. He was the founding father of modern statistical science, the creator of quantitative and population genetics. His achievements can be found simply by following his name. Fisher's equation, Fisher's exact test, Fisher information, Fisher's z-distribution, and dozens of other scientific theories carry his name. But of all his legacies, none inspire quite so much as his ability to make the best.
And I remember very well my excitement as a student when I first saw one of these electrical machines doing division all by itself. You press the button, the word backwards and forwards, and out came the answer. The millionaire computer was Fisher's own purchase. When he was appointed here in 1919, he shocked the director by saying, "What I must have is a calculating machine." Such a thing had never been heard of.
At Rothamsted, the search for certainty enabled British farmers to maximise their productivity, and Fisher's methods were swiftly adopted worldwide. Fisher thought of himself not as a statistician, but as a scientist, and in 1929 he was elected a Fellow of the Royal Society in recognition of his achievements at Rothamsted.
He was someone who was fascinated by biology from a very early stage of his life, but he also was a very good mathematician, and somehow he realized that he could apply his mathematical insight to biological problems, and this was something which really opened a whole new world for him.
From a professorship at University College London, he went on to teach at Cambridge.
Yes, he led a double life from the beginning. It was both genetics and statistics. There was never any cessation.
Anthony Edwards is a Fellow of Caius, Fisher's College, and was his last undergraduate student.
I'd heard this name, but I could see no reason why this famous statistician should be teaching genetics. And in any case, I thought he must have been a contemporary of Isaac Newton's. It hadn't occurred to me that this man might still be alive. I just turned up on spec, as it were, in the afternoon, and when I went through the open door of the Department of Genetics to ask for the person whom I'd been told to go and see, I thought he was the hall porter.
His appearance held clues to the roots of his genius.
He was a short man, a wiry, tough man, bearded, pipe smoker. He had very short sight and had always had very short sight, and one of the things I keep in my room in college was his last pair of spectacles, and I thought you might like to see how very, very small and how the glass is very thick at the edges appropriate for somebody who was extremely short-sighted.
His capacity to imagine, to visualize multiple dimensions of geometry gave him a unique perspective.
He had to depend very much on learning by ear, and he did develop the most extraordinary ability to do complex mathematics and complex geometrical arguments in his head without writing things down.
It enabled him to make intuitive new connections across areas of science which had been considered distinct. As a biologist and statistician, Alan Graffen shares Fisher's range of interests.
Fisher thought in pictures, and he solved very complicated problems using pictures in his mind. It's possible to imagine that because he couldn't see very well out there in the world, he turned his eyes inward and saw very clearly in his mind. The formulae came out of some deep recesses of his subconscious.
Fisher went up to Cambridge in 1909. His extraordinary insight inspired even his earliest achievements.
When Fisher came up to Caius as a scholar, he will have been allocated a room, and as a scholar it will have been in one of the inner courts, and as it happens, the room in question is next door to the staircase that I'm on now. With that splendid naivety which your 20-year-old will have, he will have just set off on a course solving problems in a way which will have been entirely original to him. And although the method of maximum likelihood can be found in earlier works, it is the development which started on that staircase in 1912, which led to his great 1922 paper on the mathematical foundations of theoretical statistics, from which the modern theory of estimation flows.
The concept of maximum likelihood is one of his best-known developments and is still at the cutting edge of the science's search for certainty.
Any method of estimation in statistics, such as the method of maximum likelihood, is a method to teach us how to extract information from data, to find out what we don't know from what we do know in form of data.
At the British headquarters of the Human Genome Project, the Sanger Centre in Cambridge, Richard Durbin leads the team of statisticians.
Ideally in science we want to establish the truth conclusively. Often we only have partial sorts of information. And one of the challenges is how to put together partial information that may not be completely conclusive in itself to give as much certainty as possible. The human genome contains the information that is inherited, that creates a human being from a fertilized egg. And we can think of that as a parts list and an instruction manual for putting together those parts to make a complete human.
Scientists now know the complete human genome sequence, but the code needs to be translated into a usable form. This means analyzing the individual genes which make up its component parts.
When we look at the genomic sequence, it's a long string of A's, C's, G's, and T's, just 3 billion letters long. Within that, we know there's around 50 to 100,000 genes, and these are comprised of small segments of the sequence.
Using statistics, Durbin's task is to investigate the nature of unknown genes by applying data from genes which are already understood.
What we want to do is use all the information and evidence that we have to help us find and characterize genes in other parts of the genome where we haven't yet done any experiments. The way we do that is by fitting parameters to a model using maximum likelihood or related techniques. And really the theoretical foundations for this sort of approach were set earlier in the century by Fisher and his colleagues.
He did not tolerate fools gladly, and he could be quite rude. But that is human.
Himself.
He had this amazing analytical ability to complete long mathematical arguments in his mind without putting anything down on paper. And frequently he would produce an argument which was correct mathematically and then not be able immediately to reconstruct how he'd arrived at that